So my name is Timothee Masquelier, and I am a researcher at CNRS in France, and I work on spiking neural networks. And the topic of my talk today is supervised learning in spiking neural networks. Can you all hear me fine? Yeah?
I believe so.
Okay, let's go on. So before we get started, I want to thank my main collaborators. I mean, I have many collaborators, but here are the ones who worked on the projects I will talk about today. So Romain Zimmer was a master student in my lab last year. Thomas Pellegrini is a researcher and a professor at University of Toulouse, and he works on audio processing. And Saïd Reza Kalpiche did his PhD under my supervision, and is now SBU professor, and I guess he's in the audience. Saïd, can you hear us? Okay, maybe he cannot answer, I don't know. Anyway.
Saïd is not Saïd is not in your talk.
He's not in the audience? Okay, never mind. So here's the outline of my talk today. First, I will present spiking neural networks, and I will explain why they are important tools for neuroscience to understand something about the brain. Then I will also explain why spiking neural networks are appealing for artificial intelligence. And then I will talk about backpropagation, which is a star of supervised learning algorithms in artificial neural networks, but which can also be adapted for spiking neural networks. So let's get started. Why SNNs are good modeling tool for neuroscience? Because unlike the more conventional types of neural networks, which are artificial neural networks, the spiking neural networks can capture additional things. They can capture dynamics. So if you're interested in transient brain activity or in oscillations, for this to capture this, you need a spiking neural network. If you're interested in fast processing, where most neurons fire very few spikes, maybe at most one spike per neuron, then an artificial neural network, which implicitly assume rate coding, is not suitable here because the rate is not defined when you have very few spikes. And they can also, the spiking neural network can capture an important neuronal function which the ANN cannot, which is called coincidence detection. And I think this is a very important neuronal function in the brain, and it matters a lot for computation, so I'm going to explain it better. So consider that you have a neuron here that you see in blue, and this neuron has two afferents, and the afferents send the same input spike trains, but the second afferent is delayed in time. So you have 3 spikes from the first afferent, and the second afferent sends the same 3 spikes, but a bit delayed in time. You have a small delay D. Well, I'm not going to go through the math, but you understand easily that if D is small enough, what you see on the right here, you will have, the neuron will receive pairs of synchronous spikes, and each pair will cause the threshold to be reached. So you will have 3 postsynaptic spikes there. And conversely, if D is too big, then you will have no postsynaptic spike at all. So you see that D has a major impact here on the postsynaptic activity, which is not captured in a rate-based model, because a rate-based model, for a rate-based model, the input rates are the same whatever D. So the input a rate model would predict the same output, whatever D. So the rate-based models, such as artificial neural networks, do not capture this crucial mechanism for brain function. So I think we should avoid them. The problem with spiking neural networks is that they have many parameters, and tuning those parameters can be time consuming. They have even more parameters than the artificial neural networks, because in addition to the synaptic weights, they have integration time constants. For instance, they have delays. So they have additional parameters, and tuning all of these parameters is a complex problem. So this is why I suggest that supervised learning can be helpful, because it can find the parameters that best, for instance, implement a given function, for example, object recognition, using minimal resources, neurons, energy, and time. This is a classical supervised learning problem. Or it can also be used to fit some electrophysiological recordings. And even if the supervised learning algorithm is not biologically plausible, the resulting model can be. The brain may use other mechanisms to lead to the same final network. But even if we don't use the same learning mechanism, if we still lead to a realistic model after training, I think it can be useful. But of course, if the training is not realistic, it cannot explain learning or development or reorganization in the brain. But using this approach, I think we can answer some fundamental neuroscience questions. Like, for instance, we know that in the brain, different neurons use different time constants, integration time constants. There is a broad range of time constants. And I suspect this is optimal for processing, and supervised learning approaches could confirm that. Another topic that we can study using this approach is, I suspect there are functional advantages of having plastic delays. We know that in the brain, the conduction delays between neurons are plastic, because they depend on the level of myelin, which is plastic. And I suspect this has some function as well. We can also try to infer what are the main design principles of sensory systems. What are they optimal for? Are they optimal in terms of speed, in terms of energy consumption, in terms of number of neurons or synapse or total axonal length? This sort of question, we can tackle them using supervised learning. Okay, that was for neuroscience, but I think spiking neural networks are also appealing tools for artificial intelligence. And why is that? Because they have more computational and representational power than the classic deep learning, which uses artificial neural networks, because we have an extra dimension, which is continuous time. Essentially, the deep learning deals with static activation patterns here, whereas the spiking neural network deal with spatiotemporal spike trains. So we have an additional dimension there. And of course, this dimension is particularly appealing for dynamic inputs, sounds or videos, because the input evolves through time. So it makes it particularly appealing for a spiking neural network. Of course, if you really want to exploit the advantages of spiking neural networks, you should run them not on software, but on dedicated neuromorphic chips, like IBM True North, Intel Loihi, or BrainChip Akida. And on those chips, we can have very efficient distributed and event-driven computations, which are very low power, especially if the spikes are rare, as in the brain. And because consumption is usually related to the number of spikes. So if you have very few spikes, the consumption becomes very low, the energy consumption. And it's also more efficient if the connectivity is sparse, which also seems to be the case in the brain. So it's a different style of computation if you compare to deep learning, which uses synchronous dense tensor products on GPUs and which are much more energy hungry. All right, but now I hope I have convinced you that the SNNs are interesting for both neuroscience and for AI, but the question is how to train them. So it's been known for a few decades now that you can train them efficiently in an unsupervised manner using spike timing dependent plasticity. I think you will have another talk about, at least one other talk about STDP by Professor Mohamed Ganj-Tabesh. So I'm not going to talk about it at all. You can train them using reinforcement learning. One option is to use reward modulated STDP. Again, I'm not going to talk about that. But you can also train them using supervised learning by adapting Backprop. And I am going to talk about that. And first, what is backprop or backpropagation? Backpropagation is a supervised learning algorithm for feed-forward artificial neural networks. The idea is it's a fitting algorithm. So you define a cost function, which I call L, which is the distance between the actual and the desired activations in the last layer. For instance, you can use a mean square error or the cross entropy. The idea is you have a desired activation there, and you would like your network to reach this level of activation. And the tunable parameters are the synaptic weights, and you tune those parameters in order to minimize the cost function. So basically, you move the weight in the opposite direction of the gradient of the loss with respect to the synaptic weight. And the tour de force of Backprop is that all these gradients are easy to compute in the last layer, because this is where you have a notion of desired activity. But they were not so trivial to compute in the hidden layers, because then you don't know what, you don't have a desired activation there. And the tour de force of Backprop is that all gradients can be computed recursively backward using automatic differentiation. And this will become clearer maybe in a few slides. So Backprop, short for backward propagation of errors. Okay, so why is Backprop so efficient? Because it solves the credit assignment problem. So basically, it tells what the hidden layers, what they should do, which is not a trivial problem. Another way to say the same thing is that it optimizes the features that are extracted by the hidden layers and the classifier, which is the last layer. Those bricks are optimized jointly, not independently. Another cool feature is that the number of layers is arbitrary. So of course, this opens the door for very, very deep networks, and this has led to the deep learning revolution. So this motivated us and others, of course, to adapt Backprop to spiking neural networks. And I'm going to talk about two main projects here. One is using a method which is called the surrogate gradient learning. And another one is a proposition by me and Saïd Reza Kerat-Piché to use a latency-based backpropagation. So how does the surrogate gradient learning work? In essence, the main idea is to train a spiking neural network with backprop through time. To do that, you have first to discretize the time. It does not work in continuous time. We have to discretize the time. We choose a small time step. And there is a difficulty, which is that the firing threshold of a spiking neuron causes some optimization issues. And we'll talk more about that. But to overcome this issue, we use a surrogate gradient, not the true gradient. And in practice, it means we are able to train a spiking neural network using automatic differentiation in packages like PyTorch or TensorFlow, which is really convenient, as you will see. So I'm now going to talk about a spiking neuron model, which is the most commonly used one, and which is called the leaky integrate and fire neuron. So I'm first going to define its equations in continuous time. So in continuous time, you have two equations here. The first one is the differential equation that the neuron obeys. So here U is the potential of the neuron in volts. I is the input current, and you have tau, which is the time constant of the neuron, times multiplied by the derivative of the potential with respect to time, equal minus the potential plus the input. So the first term minus the potential is called the leakage term. So and because of this term, if you don't have an input, the potential decays back to zero exponentially. And the second term is an input. It's an input to the neuron, and in case of spiking neural networks, the input is usually a spike train. So it's made of, it's a weighted sum of Dirac delta functions. weighted by the corresponding synaptic weights. And here we use a very simple synaptic model. The synapse is said to be instantaneous, so there is no time constant in the synapse, but the surrogate gradient learning method can be adapted to non-instantaneous synapses, but here for simplicity, I just consider instantaneous synapses. So equivalently, you can also describe the system by saying that each input spike causes an instantaneous increase of potential. The potential is increased by the synaptic weight corresponding to the synapses, to the synapse through which a spike arrived. And if you have no input spike, then you just have the leakage term that decays the potential back to zero exponentially. And of course, you have a threshold, and if the threshold is reached, then you fire an output spike and the potential is reset to zero. Okay, so those are the equations in continuous time. But as I said, we want to apply backprop through time, so we need to discretize the time. So here are the equivalent equations in discrete time. So in discrete time, the main differential equations become like that. You have the potential at time step n+1 equals the potential at time step n multiplied by beta, where beta is the leak coefficient. It's equal to exponential minus delta t. Delta t is the time step over tau. Actually, this part of the equation is actually exact. There is no approximation there. If you integrate the differential equation between t and t plus delta t, you would find this leakage coefficient. Then you have the input, and here we make an approximation. So here we consider S here is a binary tensor, which contains all the spikes that arrived at this particular time step. So here it's binary, n is a time step. And of course, we need to ponderate those spikes by the corresponding synaptic weights. So we multiply by W here. So why is this an approximation? Because basically we ignore the times of the time of arrival of the spikes inside the time bin. Okay, we consider them synchronous, which is of course an approximation. And for this reason, the time step should not be too big in front of tau. It should be smaller than tau for the approximation to be valid. And then here it's just a reset term. We'll see that in a second. This is just a reset term when we have output spikes. So at each time step, we check if the threshold is reached. How we do that? We apply the heaviside step function to the potential minus the threshold. And if this is more than zero, then we generate an output spike, otherwise we don't. And if we have an output spike, then we need to reset the potential. So this is done through this equation. Basically, we subtract the threshold to the potential. Okay. So here, this is actually a recurrent equation because potential at time step n+1 is defined as a function of potential at time step n. So this is a recurrent relation, and it should make you think of recurrent neural network. And this will be clearer with the next slide. Actually, we can unfold this recurrent equation through time, and this is this is a result that you see on that slide. So here the x-axis is time, and the y-axis are different layers of a spiking neural network. And so you see here, for instance, this is the input layer. Here you see the spikes of the input layer at time step 0, time step 1, time step 2. And those spikes are going to influence. On this computational graph, I represented all the different influences. So the spikes that enter at time step 0 are going to influence the potentials in layer 1 at the next time step, so at time step 1. And of course, through a weight matrix, which is the weight matrix of the first layer, W1. So this is this influence. Then beta here is the leak coefficient. So basically the potential at time step 1 is beta times the potential at time step 0. Theta here is the firing threshold. So at each time step, you check if the potential is more than the threshold. If it is, then you generate a spike. Otherwise, you don't. And theta here is the heaviside step function. And importantly, it's not differentiable, which we will come back to this point. Here it's a reset term. So if you have a spike at a certain time step, it will reset the potential at the subsequent time step. And those spikes that are emitted here, they will impact the layer number 2 at the next time step, and so on and so on. So the idea is to unroll the network through time, like we did here, so that we get the feed-forward network. And once it is feed-forward, it can be trained with Backprop. And those two steps, unrolling the network and train it with Backprop, is called Backprop through time. But as I said, there is a difficulty here, which is that the heaviside step function is not differentiable. Actually, it's not that it's not differentiable. Here you see the heaviside step function in blue, and you see its derivative in blue here. And its derivative is 0 everywhere, almost everywhere, but in 0 where it is infinite. So basically, you cannot use it when you compute the gradients in the backward path of backpropagation. You cannot use this function because its derivative is 0 everywhere, almost everywhere, but in 0 where you cannot compute it because it's infinite. So you cannot do backpropagation with it. So what an idea that has been suggested, not by me, but by Neftsi, Mostafa, and Zenke, I put the reference down there, and others, but is instead of using the true derivative of the heaviside step function, we are going to use the derivative of a sigmoid. So it's an approximation. It's like it's important to understand that when we do the forward pass of backpropagation, we use the real step function, the real heaviside step function that you see in blue. But when we do the backward pass of backpropagation, we pretend that a sigmoid was used in the forward pass. It was not, but we just pretend it was. So it feels a bit like a hack, but in practice it works very well, and we are going to use this hack. Another thing I am very interested in are delays, conduction delays between neurons, because we know that delayed dynamical systems have richer dynamics. So this is in terms of dynamics. In terms of computational power, we know that they also increase the expressive power of spiking neural networks, because thanks to delays, neurons can detect spatiotemporal patterns, not just synchrony patterns. So this is an example here by Izikevich. Here you have 3 input neurons, B, C, and D, and 2 output neurons, A and E. Between them, you have a bunch of delays. Well, if you hit B, C, and D at the same time, then both A and E will receive asynchronous spikes. So none of them will reach threshold. But if you hit first D, then C, then B with a certain lags, then A will receive 3 synchronous spikes. So it will generate an output spike. And conversely, if you hit first B, then C, then D, you will, then A will not fire a spike, but E will. So you see that the neurons start to detect not just synchrony pattern, but complex spatiotemporal patterns. So it's more interesting. So we wanted to add delays in our networks. So how did we do that? We used a temporal convolution to model the delays. So let's say that you have a certain layer L and a subsequent layer L+1. And here I have represented several connections, and each connection has a weight and a delay. So the delay records that we work in discrete time. So the delay has to be multiple number of time steps. Between 2 neurons, you can have multiple connections, each one with a certain weight and a certain delay. Well, we are going to represent all those connections by a temporal kernel. So here on this kernel, you see here the space, so the different input neurons, and here you see the time or the delays. this connection here with a weight 3 and delay 4 is represented here because the delay is 4 and it concerns this input neuron. Conversely, this one here represents this connection with the weight of 1 and a delay of 1 as well, and so on and so on. And then to compute the input of this layer, L+1, we just convolve the output of the preceding layer with this temporal kernel. Since we wanted to explore a broad range of delays, and we don't want to use a kernel which is too big because it would overfit, we use actually dilated convolutions. So the concept is that basically you force some kernel coefficients to be 0. You do not train them, they remain at 0. And this is a way to be able to explore a broad range of delays and not having too many learnable coefficients. All right, so we applied this network to a data set which is called the Google Speech Command. And the idea is to be able to classify, it's an audio data set. You have several words that are pronounced by several users, like yes, no, up, down, and you have to classify those different words. Okay, I'm not going to give you too much detail. So the input of the network was a spectrogram representation of the input sounds. So you see an example here. So what is a spectrogram? Well, the x-axis is the time. So you have the different time steps here. And the y-axis is the frequency. So, and for each time step, you have the energy in each frequency band. And this is what is going to enter the network. And then we have 3 convolutional spiking layers. An interesting aspect as well is we can, in the loss function, we can penalize for spike activity. So we can encourage the network to do the classification with as few spikes as possible. Then we have a fully connected layer that did the readout and that predicted the category of the word. This is an example of one word that is pronounced, is the word off. So you see the spectrogram of this particular word. Here you see the spikes that are produced by one channel in the first layer, in the first convolutional layer. You see the spikes produced by one channel as a function of time. So this is a binary tensor, as I explained, because you have either a spike or no spike. Here is the activity that you get in the readout layer. So the readout layer in this model was the only non-spiking non-spiking layer. Here we just use the potential of each neuron to make the decision. So this is a potential for the 12 neurons, for the 10 neurons representing the different categories before learning and after learning. And after learning, you see that you have usually one neuron that responds more strongly to the word, and usually it corresponds to the neuron which has a good category. And we decided, on this particular example, we decided based on the mean potential of this neuron. So we took the neuron that had the maximum mean potential, and we affected its label to the stimulus. And using this approach, we got a test accuracy of 94 using a spiking neural network. And if you compare with standard deep learning, which is state of the art on this task, it reaches about 97%. So we are very close to the state of the art, yet we used a spiking neural network with a low average firing rate, only 5 Hertz on average. So we were really happy about those results. And we published them in the form of a tech report that you can see on arXiv, and also the code is available on GitHub. Okay, so in terms of pros and cons for this approach, I think one of the main advantages is that it solves the spatial and temporal credit assignment problem. So basically what the hidden layers should do and when it can find the signature of each pattern. It handles it can handle deep network, both dense and convolutional layers. It can handle delays. It can train other things than the synaptic waves. For instance, it can train the integration time constant. It's agnostic about rate versus temporal coding. Basically, you don't tell the network which sort of coding it should use. It will choose, Backprop will choose. It could be rate coding, it could be temporal coding, it could be a mix between the two. Maybe different layers could use different sort of coding. It's very cool because you do not impose. You can use, as I said, regularization to encourage, for instance, sparse activity, very few spikes, or fast processing, and so on. And in practice, it means a spiking neural network can be trained using frameworks like PyTorch or TensorFlow. What is really nice is those frameworks make use of automatic differentiation, so you don't have to compute the gradients manually. The software will do it for you. We use state-of-the-art gradient descent algorithms like ADAM. We make use of CPU or of GPUs if we have on the system. And there is a large community of users. Of course, there are also disadvantages. The main one, I would say, it's memory hungry. It's linear with the number of time steps. So this may be prohibitive. We do not take advantage of highly sparse tensors. This is a shame, I think, because the spike tensors, as I said, are binary, but most of the time step, most of the neurons are silent on most of the time steps. So this tensor contains mostly zeros and a few ones, and we do not take advantage of this. We multiply a lot of things by zero. And I would say that this sort of learning is not hardware friendly. It would be hard to implement on a neuromorphic chip. For now, my approach is more use this sort of training to train a network offline on a computer, and then maybe use a neuromorphic chip to do the inference only. And I don't think it's biologically plausible, so it cannot explain learning in the brain. All right, so that's it for the first way to do backprop in spiking neural network. We're going to talk about another one now, but before we get there, I want to explain the fact that some SNNs can do fast computations with at most 1 spike per neuron. So this is useful if you want to process static stimuli very rapidly. You can use a latency coding scheme where the most activated neurons fire first and the less activated neurons fire later or not at all. And I'm going to give you an example, which is ultra rapid visual categorization. So the lab where I am in Toulouse is famous because it has demonstrated that the speed of processing in the human visual system is much more than what we thought it was before. And to convince you, I'm going to show you an example where it's a saccadic first choice experiment. I'm going to flash 2 images on the screen. One will contain an animal and one will not. And I'm going to ask you to move your eyes towards the image that does contain an animal.
Excuse me, doctor. There is a question, if you have a time to answer it.
Yes.
So I'm going to read it to you. At the beginning of the talk, I think you said that in deep learning, we can't have time. I think we can use, for example, LSTM or RNN networks, consider time. Can you explain more about this? What's the difference between using SSN networks or other recurrent networks?
Yes, you're totally correct. The recurrent neural networks in deep learning, they also have time. I would say one difference is that in spiking neural networks, we can use continuous time. Of course, with the surrogate gradient learning method, we did not for training, but in any case, as soon as the network is trained, to do the implementation on a chip, we can use continuous time. We do not need to use discrete time. So that's the main difference in my opinion.
So was your question answered? Well, I hope so. So continue, please.
Okay. Okay, so here I flashed two images. There was one animal on the left, one on the right, one on the left, one on the left. So I think for most of the people, it's an easy task, and you can do it more rigorously in the lab. And you can record eye movements using an eye tracker, and you can show that in as little as 120 or 130 milliseconds, the eyes can move towards the animal. And it's even faster for faces. If you do face, non-face categorization, you have saccades at 100 milliseconds. So it's very, very fast, especially because this is a behavioral response. So it's not only visual processing, you have to include the motor delays. It includes the motor delays here. So if you want to know if you want to estimate the duration of the visual processing, you have to subtract the motor delays. So it means in 100 milliseconds or less, the image is processed. And it's a high-level visual task, animal, non-animal categorization. So probably the inferotemporal cortex is involved. And if you know a bit of the anatomy, this is monkey anatomy. The inferotemporal cortex is about 10 synapses away from the retina. And you can, in monkey, you can do electrophysiology. You can record IT neurons. And those studies confirmed that in IT, you have responses already as early as 100 milliseconds after the stimulus onset. You have responses in the inferotemporal cortex that are already diagnostic, that are already selective. Okay, and this is extremely fast because since there are about 10 layers between the retina and the inferotemporal cortex, and those inferotemporal cortex should provide a response, a selective response at 100 milliseconds after stimulus onset, it leaves about 10 milliseconds of processing per layer. And since the firing rates are barely above 100 Hertz in the visual system, it means in the small time window that they have to do their computations, the neuron can fire at most one spike. Of course, they can fire later spikes, but the spikes will not be used by the decision making that you used when you decided to move your eyes left or right. So to do this task, you use at most one spike per neuron. It excludes the recruitment of feedback loops because there are extensive feedback connections in the visual system, but you did not have time to use them for this ultra rapid visual categorization task. So we decided to set up a line of models which respect those temporal constraints. In terms of architecture, we use feed-forward convolutional architectures. So those architectures are very classic now, so I'm not going to describe them. Our originality is that we use spiking neurons, and we use at most one spike per neuron. So in those networks, we have used STDP learning, but here again today I'm going to talk about supervised learning with Backprop, and Backprop can be adapted to this sort of network. Before we get there, you need to understand the concept of intensity to latency conversion. So you have to imagine that the network is at rest before being presented with an image. So then the neurons all start from a potential of 0. And then this is a situation if the stimulus is weak, you may never reach threshold. If the stimulus is a bit stronger, then you will have a spike at a certain time. But if the stimulus is even stronger, you will have an earlier spike. So it's pretty simple, but it's different from the conventional view, which is that the intensity is somehow converted into rate. here it's converted into a latency. And with this simple concept, you can encode a spatial stimulus into a spatial temporal spike wave. So for instance, this stimulus will lead to this particular spike wave, and another stimulus would lead to another spike wave. So the spike wave is a signature of the stimulus. And so we adapt to this sort of network. So here you see, and this project is called S4NN, Single Spike Supervised SNN. So this is a work that has been done with Dr. Gerard Pichet. It's just been accepted in International Journal of Neural Systems. So it's in press. In the meantime, you can read it on arXiv, and we also published the code. So the idea is we have at most one spike per neuron. In the input layer, we have this intensity to latency conversion. So here we used NIST digits for the data set. So the brightness of each pixel is converted into a latency. The brightest pixels fire first. And we have at most one spike per neuron everywhere. So each neuron has a single latency. And in the output layer, we have this notion of desired latencies, the dotted lines, and the actual ones. And between them, we measure an error. And this error is backpropagated through the network. Importantly, we use very simple neuron model. It's the integrate and fire neuron. It has no leak. So it is the simplest neuron model you can think of. It has no leak. And at most one spike per neuron. So basically, and it uses instantaneous synapses. So here is the voltage as a function of time. Each time you have an input spike, the threshold is increased. When you don't, there is no leak, so it remains constant. And at some point, it will reach threshold and generate an output spike. So we have a certain latency here. Okay, so can we adapted Backprop to this sort of network. For this, we had to make approximations. So I'm going to explain this a little more here. So for now, I'm going to consider the derivative of the loss with respect to this particular weight, Wji, between neuron I and neuron J. For each neuron, we can define a latency. There is a single spike, and we denote its latency by Ti, the latency of neuron I. So first we use the chain rule as in normal Backprop. So basically we say that changing W here will change the loss, but there will be intermediate steps. So it will first change the voltage of this neuron, J, Vj. Then changing this voltage will influence the latency of J. This is this derivative. And ultimately, changing this latency of J will change the loss. So this is a chain rule. The first term is just a notation. We call it delta J, as in normal Backprop. The second term here, you should pay attention. Here, we want to compute the derivative of the latency with respect to the voltage. And this derivative is impossible to compute, so we had to approximate it. So basically, we said, okay, if there is if J fires a spike before the end of the simulation, before Tmax, then it means increasing the voltage would probably lead to an earlier spike. So we know that this relation, this derivative is negative, but we don't know its magnitude, so we only kept its sign. So it's a very crude approximation, but this is what we did. And otherwise, if we have no spike in J, it means probably changing the voltage would not generate a spike, so this derivative is 0. And so this is for the middle term. And the last term, this is just the influence on Wji on the voltage, and it's one if I fired before Tj, then you have an influence of the synaptic weight. But otherwise, if I fired after Tj, changing the weights will not change the potential, so the derivative is 0. So this is the first step. The second step is to apply a total derivative. Now we want to compute delta j here as a function of the deltas on the subsequent layer. So to do that, we use a total derivative. So K is the indexes for all the neurons that J touches. And we say that the derivative of L with respect to DJ is a multiplication of the derivative of the loss with respect to TK, where K is the latency, TK are the latencies of the subsequent neurons, multiplied by the derivative of TK with respect to TJ. So the first term here is just a notation, is delta K. And the second term here, you should also pay attention. Basically, we want to know to what extent the latency of TJ influences TK. Well, first, for the latency of TJ to have an effect on TK, we should have that J fires before TK. Otherwise, it has no influences at all. And if it has an influence, well, you don't really know how to compute this. But what we know is that if the synaptic weight is 0, this influence is 0 as well. And if the synaptic weight is strong, then changing J will have a strong influence on changing the latency of K. So it means this term should be bigger. So we just assumed a linear relationship. That is, this term is proportional to WKJ. And since we rescale the gradients with the learning rate anyway, we don't need the proportionality factor, and we only kept WKJ. All right, so this is an approximation, but here we sum all the indexes of the neurons K that fire after TJ. And using this approximation, we could compute the gradients everywhere in the network. This is a recursive formula. And unless J is an output neuron, in that case, the loss is defined on the output layer. So it's very easy to compute the delta for the output neurons. We have this concept of desired latency, and we use the mean square error to compute the difference between desired and actual latencies there. So as I said, we tried this approach on the NIST data set. And we also compared, so we reached an accuracy of 97.4. If we compare to other fully connected spiking neural network, our accuracy is on the average. It's not the best. It's normal, but I would argue that our neuron model is much simpler than the neuron models that were used in those other papers. So it's much more hardware friendly. Another thing that I like about our approach, it can lead to very fast decisions, because as soon as we have a spike in the output layer, we can decide the category of the stimulus based on the category of the first neuron to fire. So we don't need to continue the processing. We can stop the processing before most neurons have fired. So to conclude with this second approach, I think the approach is interesting from a neuroscience point of view and from an AI point of view. For neuroscience, well, the trained model is compatible with the speed of processing in the visual system, because we have at most one spike per neuron. And for AI, it's an appealing model because inference can be done efficiently on low power neuromorphic chips with at most one spike per neuron and much less on average. So that's it. I want to thank you for your attention, and I'm ready to answer questions if you have any.
So thank you, Doctor, for the time that you have given us. Let's hear the questions if there are any.
I have some questions.
Okay, please.
Okay.
Thank you, Doctor, for your interesting presentation. I have some question about approximating the derivation of step functions. Actually, you mentioned that we can use some sigmoid function
yes.
to approximate this function, and actually we approximate its derivative by make a derivation from the sigmoid function. But
yes.
In mathematics, we have a definition of some fractional derivation, and we can make a fractional derivation in some non-smooth functions like a step function. Would you like using? Would you please tell me using the fractional derivation can help to improving the accuracy of learning when we are approximating the derivation with some other definition of derivation.
Okay. Well, thanks for the suggestion. I admit I do not know about fractional derivation, so I will I will take a look. Just one comment. Maybe I insisted too much in my talk in the problem of non-differentiability, but in practice, the main problem we have is not so much that the function is not differentiable in zero. It's more than the gradient is zero almost everywhere. It's zero everywhere, but in zero. And this in practice is the biggest problem we have, because it means all the gradients are zero. All the gradients are zero almost everywhere, so we cannot apply backpropagation. We cannot when we want to the weights in the opposite direction of the gradient. If the gradient is zero, we don't move the weight, so we are stuck. And this is a bit similar to, in the artificial neural networks. Most people use rectified linear units, and the rectified linear units have the same problem. They are not differentiable in zero. But in practice, it's not an issue because the probability of reaching an activation of exactly zero is zero. So in practice, it's not an issue. And so I don't know. Maybe fractional derivation would help, but would they help in avoiding the fact that the derivation is zero almost everywhere, or?
Maybe, I'm not sure, but in some applications, fractional derivatives is more helpful instead of approximating non-smooth functions by some smooth functions.
Okay, well, thank you very much for the suggestion. I will take a look into it. Maybe it's useful, yes.
Thank you so much. Thank you for your answer and your interesting presentation.
You're welcome.
So it seems that we don't have any other questions. So thank you for your time, Doctor. And
okay. Thank you very much.
It was a very interesting presentation.
Thank you very much. Bye-bye then.
Goodbye.
Goodbye.